Okay, so welcome back, everyone. So this is going to be the second, well, I guess for the GLab, the first talk in a series of talks by Wilmer Smilde from the University of Illinois Urbana-Champaign on well, classification problems of geometric structures and relative algebroids.
Yes, thank you, Martin. Yeah. The first talk was already there. We motivated the introduction of, or even developing a theory of relative algebroids, or a theory that we call relative algebroids. And on the notes, this corresponds to roughly the first section. There you'll see examples being worked out to motivate the initial definitions of relative algebroids, and also why we're looking for a Lie theory that's missing. For the rest of this course, I roughly put a schedule for the topics we're going to do in order. First, I want to recall things about derivations in brackets, because in this part, we're really going to go into the more technical machinery and technical language of relative algebroids, and it's very heavily based on derivations. So that's what I want to recall. Then we're going to talk about relative derivations and their structure. Then relative algebroids, their prolongations, and see what kind of Lie theory we got here, how we can rediscover Lie theory. I want to go back to the illustrative example of surfaces with scalar curvature satisfies this differential equation. I don't think this is the schedule for just today. I think we're going to need the two lectures, but this is sort of the overview of what we're going to do. Okay, good. Now I'm gonna make this disappear. Maybe I'll refer back to it later. So yeah, let's start with derivations on ordinary derivations on vector bundle. So for this, we fix a vector bundle. And throughout, I'll use the following notation for like forms on the vector bundle, by which I do not mean forms on the total space of the vector bundle, but sections of the exterior algebra of the vector bundle. So definition, a K derivation on E is a map we call D on forms to forms of the degree plus K that satisfies the Leibniz rule. So D alpha wedge beta equals it's a derivation, a graded derivation. And K times the degree of alpha wedge d beta. And we use the notation derivation K of E is the set of K derivations. These K derivations are in duality with brackets. Or K brackets. A K bracket is a bracket on the sections of E that takes in K plus 1 elements, and it's skew symmetric and gives us a section back. Plus an anchor from the K E to Tm, or a symbol that also satisfies the Leibniz rule. Take sections V0, so Vk times some F. This should be F first, Vk, and then we take the derivative of F in the direction of the first K elements of E, but we can only differentiate because of this anchor. So, oh, that's not an equal sign, that's plus derivative of rho v0 vk minus 1 f times vk. Every k derivation determines a k bracket and vice versa through the Koszul formula that I'm not going to write down. Okay, some examples of derivations. E equals Tm. This is maybe a very central example for a story. We can take d to be the exterior derivative or the RAM differential. And this is in duality with the Lie bracket of vector fields. Another example is you take a Lie algebra. Consider it as a vector bundle over a point. And we can take d to be the Chevalley-Eilenberg differential. Or its corresponding bracket is just a Lie bracket of G. Corresponds to each other. In this case, that's not really Leibniz rule. Or the Leibniz rule, this corresponds to linearity. So whenever you have brackets, you have derivations. Maybe another example that's not of degree 1, because these are 2 degree 1 examples, is zero derivations on a vector bundle. In this case, we have a derivation d that doesn't change the degree. And this corresponds to linear vector fields. Oh, and the flow on the total space of E. Yeah. And it's, I think, easiest to characterize it through the flow without introducing the tangent bundle of E. With flow, it is determined by ddt. By, here's where the derivation comes in. Alpha equals y star of t d alpha, and y of 0 is the identity. So our derivation gives rise to an ODE, and this, if you differentiate this ODE, you get a linear vector field. As example / definition is, if you've seen Lie algebroids, let's just define a Lie algebroid like this. A Lie algebroid is a vector bundle A over M with a degree 1 derivation that squares to 0. So you can take this as a definition or as a set of examples. So here's where they show up. What is very important to us for the rest of the story is the structure of derivations. They look like in coordinates, maybe another kind of descriptions, the description as a module, and the relation with the symbol. So let's do that first. If you take a derivation on a vector bundle, we can look at its representation in coordinates. So we also choose coordinates x mu on M and EI, a frame of the dual, a coframe of E star, the local frame. And then the derivation is uniquely determined by its action on these E forms, as well as its action on the functions. Because of the derivation property, this uniquely determines, because of the Leibniz rule, uniquely determines the derivation. So you can write down what it is. So we get d of EI, and this is some set of functions, Ci jk, Ej wedge ek. I'm using Einstein's summation convention. This is the action on the forms, and the action on the functions is determined by dx mu equals rho mu I EI. Of course, you have a corresponding bracket. The bracket can be completely also can be defined in terms of these structure functions. These are the things we call structure functions of the derivations. They're functions on M, and the bracket satisfies Ej Ek equals Ci Jk Ei. This is in the dual basis, the dual frame of E, with anchor rho of EI equals rho mu I dx mu. So we get a map to the tangent bundle. Now it becomes clear why we choose a -1/2 over here. So that this function is exactly the structure function of the bracket. Okay, that's a local coordinate description. Let's go to the module description. Oh, sorry. Yeah, these are for one derivation specifically. You can, of course, generalize it to k derivations. Get a different factor in front. Yeah, but we're looking at one derivation specifically. Lost a nice chalk. Yes, exactly. Yeah, good point. If you square d to 0 on this side, you get a Jacobi identity on the bracket. I had a nice chalk. I lost it somewhere, so we're gonna just use the last nice chalk. Okay, so the space of derivations. Now we go back to k derivations. If you take a k derivation on a vector bundle and f a smooth function, then f times d is again a k derivation. It still satisfies the same Leibniz rule. That's not affected. And because of this local coordinate description, the module, as a module, the k derivations are finally generated and locally free, finally generated by the choice of these functions. So the Serre-Swan theorem tells us the set of k derivations is isomorphic to the sections of a vector bundle, curly dk of E, where dk E over M is a vector bundle. You can count the rank of this vector bundle by looking at the number of independent directions in your choice of functions over here. So here it's like n directions, and these have to be skew symmetric, these coefficients. So there's an n over 2, and you have to add the dimension of m and another set of n. So from this, you can read up the dimension, or the rank of the vector bundle. Yeah, so this vector bundle is going to play a central role later in the story. When we go to relative derivations, we'll get a very nice description of the fibers of this vector bundle, but that's for later. The other part of the structure of derivations comes from the symbol. The symbol of a k derivation is it's the anchor of the corresponding bracket. I'm going to give you an more explicit formula for that later. And this is the anchor of corresponding bracket. And this corresponding bracket was defined through the Leibniz rule. So we can make this explicit by df. We acted on some function on m, and then we get a k form, I mean. So we can pair it with the b1 wedge bk. And this defines the symbol as follows. It's sigma d. Oh, it defines the anchor. This will be df wedge rho of this b1 bk. And this is well defined because of the derivation property. The symbol is C infinity of n linear. So it descends to a vector bundle map and gives rise to a short exact sequence. With that bundle of derivations in the middle. And on this side, as kernel, we have the pointwise brackets. The derivations without symbol give rise to a pointwise bracket on your vector bundle. K derivations in the middle. And it lands in the space of anchor, so to speak. So this is sigma. This is wedge k e t m. And then goes to 0. So this could be seen as a vector bundle structure this could be seen as a structure of ordinary derivations. Any questions so far? This is the amount we need to know from derivations in order to continue. There is a k plus 1 missing. Yeah. Yeah, for k equals 1. Well, for k equals 0, we get the ITS sequence. Because with the convention we use here, the derivation of the k is on the degree of the forms, which means that linear vector fields have degree 0. And linear vector fields are sections of the TIA bundle. And that's also why k derivations correspond to brackets that take k plus 1 arguments. So that's where the grading can be confusing, yeah. Mm-hmm.
I have a question.
Yes, please.
Could you, so I don't see why that first term is what makes the sequence exact. Could you say a bit about that?
Yes, I can, of course. What makes the sequence exact can be seen in local coordinates over here. The symbol will be the components of the row. And then the kernel corresponds to, well, just ordinary functions, ijk, where here jk is now skew symmetric. Yeah, good question.
Okay, thanks.
Another way of seeing it is if you get a pointwise bracket on the fibers of E that takes k plus 1 arguments with a symbol 0, it gives rise to a k derivation. Row-causal formula. Any further questions before we move on?
I'm just curious, when you use these, which degrees will be particularly important? Like, for example, besides 0 and 1, do you make a lot of use of all of them?
I make a lot of use of 2 as well.
2.
I'm not sure I'm going to use it explicitly in the course. 2 plays a particularly important role, and indirectly also k derivations. If you set up a k derivation to a much lesser degree, but 2 derivations for sure, especially because the d squared is a 2 derivations. So we'll get the d squared of things, which are not actually squares, but there'll be 2 relative 2 derivations in the story that will show up.
If it takes it dark, some of all k, then the derivations will also have a bracket, right? Just
Yes. Mm-hmm.
and Smilde as something becomes something, right? The algebroid also.
It's a graded. Yeah. I think it's more in the direction of graded algebra in a super language. I don't want to make this precise right here, right now, because I don't know the specific details from the top of my head, but it's in that direction, yeah, I think. Mm-hmm. It is in a way, I mean, they correspond to linear multi-vector fields too. Mm-hmm. Okay, yeah, last chance to shoot your question before we move on. Yeah, so next part is derivations, but relative. Yeah, okay. Yeah, I'll repeat it for everyone. So Rui is saying is that a reference for ordinary derivations, also in terms of these vector bundles and their Gerstenhaber structure too, is a paper by Marius and Rich Kreinig and Moerdijk, Ike Moerdijk. I don't know the type. I don't remember the title of the paper. Well, deformations of Lie brackets. There you get it. Thanks. All right, very good. Derivations but relative. Okay, yeah. So now we start with a vector bundle again, over a base space N. And we also have a map into N, from N to N. It could be N map. But typically we want to think of it as a submersion. There are definitely important examples where this is not a submersion. And as notation, I'm going to use B for the pullback bundle. So whenever you see B, it's a pullback of A along the map that we use. And then we can introduce a notion of a K derivation relative to the map P. So relative to P is a map. It's again a map defined on forms on A forms. But its target is now not, this time it's not forms on A, but it's forms on the pullback, it's forms on B. So it may depend on extra variables if P is a submersion. Well, it's not an ordinary map, it's a linear map that satisfies still Leibniz property that we can make sense of. Alpha wedge beta equals, first we have D acting on alpha, and then we land in forms on B, but beta is not a form on B, so we have to pull it back to B to make sense of it. Plus we have a degree, a sign coming from the degrees, alpha k, and same story with alpha, we have to pull it back to B, D beta. That's the Leibniz rule. And the set of derivations relative to P would be derivations of K that are on A relative to P. That's the notation we use. Set of relative derivations. I mentioned that this definition also works for arbitrary bundle maps, because you can, if you have a bundle map, you can pull back forms from one bundle to the other. But for the sake of exposition, we stick to K derivations relative to maps. Also in the setting of relative algebroids, they will be relative to maps. But in principle, you can use an arbitrary bundle morphism. To K derivations, we also have K brackets or relative brackets. So a bracket, I'm just going to write it down for one bracket. So we still in the same setting with A vector bundle P and B the pullback, and a bracket relative to P is now a bracket that takes into sections of A and results in a section that depends on the additional variables, in the additional variables of the fibers. So you get a section of B plus an anchor that goes from the pullback and only allows us to differentiate in the directions of the base coordinates. So it goes to P star of Tn, such that the Leibniz rule is satisfied. Let's write it down. V Fw equals Vw. This makes sense as a section of V. F, however, is a function on N on the base manifold. So to make sense of this, we have to pull back F to a function on N. And then there's a derivative part. So we want to differentiate f in the direction of v using the rho. But rho's defined here. So we pull it back. V star v. This works. And we have to pull back w as well. Let's see if everything makes sense. So it's okay. The spaces they live in, it all lands in here. This derivative might be a little funky. F is a function on the base n. And this anchor allows us to pointwise differentiate functions on n. But the pointwise depends on m, the bigger space. So at every point in m, we get a vector tangent to n. So while f is a function of n on the base space, this derivative lives on the total space of the submersion. So this thing will be in C infinity of m, because the anchor depends on additional variables. And in this case, we have a duality through the Kosul formula. So df compared with some w, it's the same as L rho w of f. Maybe technically I want to pull this back. B star w. And d alpha, some p star v, p star w. This has the brackets and the anchor, so this is the rho p star v alpha w minus L. I'm going to run out of space. Minus L rho p star w alpha v. And then the last term involves the bracket. Minus p star alpha v w. This will add it together. So now a relative bracket determines a relative one derivation, and vice versa. So far, the story is quite similar to ordinary derivations. First, I'm explaining the parallels with ordinary derivations, but later we'll see some structural differences. So first, we do mostly the parallels. So relative derivations in coordinates. Again, this time we choose a frame of A, or dual frame of A. And we take submersion coordinates. So P will be becomes projection, x mu, y sigma to x mu. And then the derivation is uniquely determined by its action on the one frames of A and on x mu. So d of EI is some set of functions, some tensor really, x mu, y sigma. Ej wedge ek. D of x mu equals rho mu I x mu y alpha EI. I'm explicitly listing the dependence on the fiber variables. In a way, you can think of these relative derivations as derivations on the pullback bundle that are not complete. That we can only, yeah, they're not complete in the sense that we can only differentiate things that are constant on the submersion fibers because it's not specified any further. So d of y sigma is unspecified. It's not defined. So these look like the formulas that I wrote down in the last talk. Maybe I wanted to make this explicit for the set of surfaces. So we looked at surfaces whose scalar curvature satisfies the set of equations. I'm going to copy this type of equations we have. And d theta 3 was k theta 1 which theta 2. And dk, what do we have? Cosine phi theta 1 plus sine phi theta 2. And what we did in the introduction, we bumped up every part of the structure to independent variables. So the theta 1, theta 2, theta 3 constituted a coframe on a vector bundle, and this d became an actual derivation. So the Ram differential became a derivation on this bundle. We bumped it up to an independent thing. So in this special example, P sends k phi to just k. And A star equals R3 is spanned by the theta 1s, the theta i's, trivial bundle R3. And in this example, only the anchor depends on the fiber variables.
Just have in classical differential geometry, a submersion
Mhm.
from what did you call it, M to N?
Yes.
And if we just think of what a relative derivation would be. So you're saying that you have the total space of the fibration. A degree 1 derivation or derivation would basically just be a vector field on. It would be like a vector field on M. It's just that it's only defined on functions that are invariant, that are basic.
Mm-hmm.
So it's a vector field on M,
Yeah.
which is partially defined
Exactly.
on a subalgebra of basic functions.
Mm-hmm.
But is that accurate?
That's very accurate. Yeah. Or maybe you can think of basic forms. You can think of, instead of on M, you have maybe some.
The tangent would be. But take A to be the tangent bundle of N.
Tn, and that's with the pullback. Tn.
Yeah, so what would a relative derivation be in this context?
A relative zero derivation, that will be a relative vector field. Oh wait, a relative linear vector field. So for, yeah, that's true. You don't need this to be the tangent bundle at all. For this, that's A, B.
B is the pullback.
Yeah, B is still the pullback of A.
As simple as possible. So
A relative vector field gives rise to a relative one derivation. Let me tell you what a relative vector field is. Maybe I can try to make up this example. Okay, then A will be R. So I think that's easy. That's simple enough. So relative vector field is it's a section of the pullback bundle, the pullback tangent bundle. So in a sense, we only know how to differentiate in the n directions, not in the direction of the total space. You can still make sense of integral curves for this vector field. It will be a curve in M integral curve would be gamma going from some interval to the space M such that the derivative at each point is x, but only after projected back to M. So gamma dot at t will be the x at gamma of t, but we have to project, this one lives in M, this one lives in is tangent to N. So you have to project it back to N. That will be an integral curve. It's not uniquely determined. Yeah. So let's see what kind of relative algebra we get. We can look at the R, trivial bundle over N. Look at R over M. And now we need to specify, so basis of R is, well, let's do R star is dt. And then we write the derivation as d of dt equals 0. Well, it has to be 0 if it's a one derivation. And then d of some coordinate functions. Oh, d of any function m will be Lx of f, and this is now in times dt.
sorry, what is what is f here?
F is a function of n.
Derivation. The derivation is capital D.
Derivation is capital D. Oh, sorry, yeah. It's capital DF. And this is the algebroid, the relative algebroid of a relative vector field. We can write, I think I want to write this in the submotion coordinates too, because this is a one derivation. Yes.
So X is a section of the pullback tangent bundle.
Yes. So again, this thing will be the function of m.
So what does Lx of f mean?
So yeah, we can pointwise differentiate in the direction of n. So Lx of f at a point m, this should be df paired with x at the point m, but this is the derivative at the point p of m paired with x of m. Maybe I'll write it down in coordinates too, so it might be a bit more clear.
I never realized that if you have a section of the pullback tangent bundle, right, that I never really thought of that as being able to differentiate anything, because it's not a tangent vector on n, so it's not a vector field on n, so we can't differentiate functions on n. What you're telling us is that if the function is pulled back from the base, then it does make sense to take the derivative of that function.
Exactly.
A vector field that's pulled back from n.
Mm-hmm.
The problem is you look at your compaction of x with the pullback from here.
Yeah.
It's not the same thing, right?
Yeah.
Really, the pullback of here is the
Yeah.
pullback tension on.
Mm-hmm.
Okay, and so what did you do? You took this one relative vector field,
Mm-hmm.
x, right? And now you're saying there is a relative algebroid
Yes.
behind it, just in the same way that if you had a vector field on a manifold, you could take the trivial of the algebroid with R and let the anchor be given by that vector field x, right? And so
Mm-hmm.
vector fields are the same thing as rank one Lie algebroids.
Yeah.
And you're just saying that there's a corresponding relative algebroid. And what is this relative algebroid? It's R and R.
So yeah, so for relative for vector fields, you get a correspondence between rank one algebroids and vector fields. For relative vector fields, you get a correspondence between rank one relative algebroids and rank one and relative vector fields. What are you saying? What's this?
What
On
are
the
you
R.
referring to as the relative algebra? Which thing are you pointing at? Say this is the relative algebra.
Oh, I haven't defined relative algebroids yet. I think that's a problem. This is the relative algebra. It's a vector bundle and a submersion with a relative one derivation. That's the relative algebroid.
Where is the anchor?
The anchor of the relative algebroid is the x. So normally for vector fields, the anchor of the vector field, the anchor of the algebroid corresponding to the vector field, to T n, this would send 1 to x. And for the relative anchor would be goes to the pullback of Tn, and then it would be 2 to x. So it sends 1 to the relative vector field. That's the anchor.
Okay, so in general, for relative algebra, we should expect the anchor to be in the pullback of the tangent bundle
Yes.
via a submersion.
Yeah.
Interesting.
Yeah.
So it's almost as if you're yeah, okay, sorry.
And if you write down the equation of relative vector fields, the ODE that corresponds to it, right? We have our x, t, y, t in submersion coordinates. And then the equation that we have is for integral curves is x dot of t equals some I'm not choosing my notation, I'm improvising, so I might have to think about notation a little. We can write down this x in submersion coordinates as some x mu, depending on two variables, x, t, y, just x, y, and then the x mu. That's my relative vector field in submersion coordinates. If you write down the ODE that corresponds to it is x dot of t, x dot mu. That's the same as x mu, xt, yt times, oh, that's it. Yeah, there's nothing more. So this is the ODE for integral curves.
Two axes there. It's a bit confusing.
Oh yeah, one is supposed to be lowercase, and this is supposed to be uppercase. And this is lowercase. Arguments are lowercase, and this is uppercase x. These are the components of my vector field. And these type of ODEs are the ODEs typically in the line control systems, where y of t is the control path, the path that you choose, and the x of t is y of t would be input, and the x of t is the output space.
But wait, sorry, so the curve that you're talking about is a curve in M, right?
A curve in M, yes, in the total space submersion.
And that curve is given by x of t, y of t.
Mm-hmm.
But you're saying that the only constraint is on the x coordinate. It's the derivative of x that is constrained by the vector field.
Exactly. And y is completely left unspecified. Actually, if you want to solve the system, you can freely choose your y, and then it has it is locally a solution. So there are many integral curves for the same point.
But how can you freely choose your y if you don't know what x is? I mean, y is on the fiber, right?
Mm-hmm.
I mean, you can't, until you trivialize it, you can't really freely choose y.
Yeah.
Not so. Like,
In a way, yes.
Don't you have to choose a path on n first, and then try to lift that path to a path on n? Anyway, you can ignore this. Keep going.
I don't think that's generally possible.
So let me just make a comment for the benefit or the confusion of the audience. Normally when we have a vibration, like a submersion, right? When we talk about relative vector fields means vector fields tangent to the fibers. But that's very, very different, opposite from what he's talking about. He's talking about vector fields, which are sections of the pullback of the tangent of the base. And so normally you don't think of those as actual vector fields at all on the total space. They're not actually vector fields at all.
Mm-hmm.
But they can be used to differentiate functions that are basic. That's the weird thing. And if you understand that concept, then he's introducing algebroids, which have that same behavior.
Mm-hmm.
Their anchor is also not a real vector field on M, but only a vector field pulled back from the base.
Yeah.
What's the relationship between these relative algebroids or relative vector fields and like the theory of connections? Like if I take a principal bundle and I choose a connection, in that case, the pullback tangent bundle actually is embedded inside the tangent of the total space.
What's the relationship between this and connections? I'm going to talk about the structure of relative derivations, and then I can comment on it as a splitting. Which I think this example of a relative vector field is definitely highlighting a lot of behavior of relative algebroids that's, I think, alien when you come from the algebroids.
this almost just the Elsman connection on your subversion and the relative vector field does become a.
Yeah, if you choose a connection, you can bump up vector fields to relative vector fields to vector fields. I'm repeating what you say because I'm not sure if the people online can hear the audience, but I think that, yeah, the connection with connections becomes more clear with with the structure of derivations.
Is it correct that if you took a function from M to another space that's sort of complementary to the one to N to sort of write it as a product,
Yeah,
then M would have then X would specify a connection on M, and then that relative ODE you wrote would be the parallel transport equation. Because then Y would be like a path in the other space.
it's a map into M that's transverse.
He's basically trying to solve
Yeah.
the problem that I brought up, which is that if you really wanted to specify y first, right?
Yeah.
You would need a projection from M to
To another
base, right?
Transverse.
Base B,
Yeah. Mm-hmm.
and then you could choose a path on that base B.
Mm-hmm. This does remind me of something I talked with Eckert about. When you have these GX, homogeneous GX structures, you have them. Yeah, you have a map into X itself from the principal bundle. That's like transverse. Anyway, that's for another time. Let's dive into the structure of relative derivations. So I'm still fixing A over N and P from N to N. And now the derivations, K derivations relative to P, is a C infinity of M module. So because FD, we can multiply with any function in M. Because the target space of this one are forms on the pullback B. So that works. So again, by the Serres-1 theorem, we get a vector bundle T1 AP over N over the total space. DK, thanks. And I get a symbol of D is the anchor. Of the corresponding bracket through the same Kosul formula that I wrote down. So just like for classical derivations, we do have this simple short exact sequence. So these are the parallels with the classical story. Wedge K plus 1 B, B, then D1 AP, and then B star Tn 20. These are parallels with the classical story. This is also wedge K and wedge K. The pullback of what? This is this part.
P is the pullback of A, is that correct?
Yeah.
P pullback of
P is already the P star of A. Yeah. So in fact, the kernel is a pullback. This entire thing is the pullback of a vector bundle on A. This side is also the pullback of a vector bundle of A. And in fact, the bundle of K derivations is a pullback of a vector bundle of A. Namely, the bundle of K derivations relative to P is a pullback of the bundle of K derivations on A. As a vector bundle. And just the symbol exact sequence is the symbol is the pullback of the symbol of the derivation bundle on A. So that's quite simple.
If you have a relative algebroid, if A is a algebroid on N,
We don't have a relative algebroid yet. This is just a vector bundle. DKA is the vector bundle whose sections is the K derivations on A.
oh, so you're saying that if you have a relative algebroid on N, like relative to P,
We don't-
you can project it to just a regular algebroid on N.
It's the pullback of so he's not talking about relative algebroids yet.
No.
But he needs this bundle of K derivations, which is like an Atiyah algebroid or an Atiyah bundle, this DK. He's just saying that the DK is the pullback of one that is on the N. If you can't keep your right the same line before the relative sections.
I mean this P star DK A is derivations K A P, and there is you can go from sections to here to sections to here, yeah. So there's a map this way. Right, the example I want to do is actually quite different from submersions. But if you take M to be a point in our, space N, and P is inclusion of the point in N. Then D, a derivation relative to this inclusion, what is it? It's a derivation that takes in forms on A and goes to, forms on the fiber. Plus 1 of A x star. And if you define D at the point, a derivation at the point x, by considering it is a section of, I'm going to keep x here. So if you take D any derivation on A, or one derivation on A, then we can look at dx equals its pullback, its restriction to this fiber. And this is now the derivation relative to Ix. So just by restriction. This gives us an identification of derivations on A relative to the inclusion of X with the pullback bundle to the inclusion of X. So that's the fiber. One of A, the fiber at X. So we have our vector bundle here of derivations, and we can think of its elements, its pointwise elements, as derivations relative to the inclusion. Yeah, so this is already a very useful way to think about, to work with elements of this derivation bundle. Another way to produce relative derivations is from ordinary derivations. So if we take a derivation on total space, we can restrict it to forms on A. And this is relative to P.
The derivation relative to P. So
Yeah,
the circle P star is an element of there.
exactly, yeah. And this process is C infinity of M linear, because the structure comes from multiplication by the right. So this comes from some map of derivations of B to derivations relative to B. So this ultimately comes from a map on the level of vector bundles, dkb to dk of P star dk of A. So you get a bundle map. And this reveals a lot more additional structure that relative derivations have. I'm going to write down the whole diagram that decomposes it in every direction. So this is part of a short, it's a surjective because of reasons that they can be found later. So for k equals 1, that we get now a short exact sequence. When we get a short exact sequence here in the middle, homomorphisms from B, the kernel dp. That's the kernel of the P star map. D1b, let's just stick with P star D1a. We get a short exact sequence this way. But also we have the symbol short exact sequences from before in this direction. So the symbol map goes down. This goes to P star hom A Tn. Here the symbol map goes to hom P star Tn. The kernels of the symbol maps are hom wedge 2b B. And here is P star pullback home wedge 2a A. And these are isomorphisms. That's something here. Oh, sorry, this is not a pullback. This is Tm. It's just an ordinary derivation. Tm. Here we have an isomorphism. B kernel of Tp. So the columns are exact because they're symbol exact sequences. And the row exactness on this level comes from the exactness of this level comes from the snake lemma eventually, because the bottom row is exact. It's easy to see on the level of some symbols. So this is also exact. So that's why the kernel is actually this bundle. And this diagram symbolizes the structure of the bundle of relative derivations. We can use a different color for this one.
So if we can remind me
Yeah.
that, what is sigma?
Sigma is the symbol map.
Oh,
It's not a nice sigma. So we send a derivation to its anchor. And here's also where connections play a role. If you want to bump up a relative derivation to an honest derivation on B, you'll need to extend the symbol only. And to extend the symbol, you need to go from Tn to Tm. So any connection induces a splitting of the bottom row, and with that also induces a splitting of the top of the middle row. So yeah, what is a connection on P? P induces splitting of rows. Okay, this is what I wanted to say about the structure of derivations. What's the setup with time? Now we're going to move to a different topic, so it's a natural place for a break. Let's just continue. Sounds good.
But you're getting to relative algebra.
Exactly, yeah.
But presumably one of these things on the board already is an example of relative algebra.
You've definitely seen examples. Everything with a one derivation is essentially a relative algebroid. Let me write it down for completeness. So an algebroid relative to a submersion P from M to N is a vector bundle over the base space as we saw with D derivation relative to P, a one derivation relative to P. So we got a triple AP and the derivation. That's essentially the structure of a relative algebroid. We still even though the b is not apparent in this notation, we still like to use b as the pullback of a. And then it fits into like a square. And to depict the derivation, I like to use a dotted arrow that goes back this way, d. And it's dotted because it's not a map. It's just a structure that takes in objects that live over A to objects that live over B. We've seen some examples already, like the relative algebroid corresponding to a relative vector field. Then A is just a trivial bundle, the trivial line bundle. What other example? We saw the relative algebroid associated to surfaces with our curvature equation. That gave rise to a relative algebroid. Change this title to. Yeah, those are kind of the examples we saw, but they're very flexible. Coordinates, we had EI frame of A star. I want to write down the coordinate equations again because what I'm going to talk about next. I just want them on the blackboard. X mu y sigma. That's our projection. And then the EI, something like this. That's the local structure of a relative algebroid. Maybe I want to stress that we can also define it in terms of a relative derivation, a relative bracket, because there's a duality between one derivations and brackets. So we can also define it in terms of an anchor and a bracket, which are both relative. Okay, next definition. It's our notion of solution to relative algebroids. We call it a realization. A realization of this relative algebroid PD. It's a manifold that realizes, it's a structure that realizes the derivation of the relative algebroid as the exterior derivative on an honest manifold. So it's a triple. Well, we need a map from the tangent bundle of P to B. So this is our map theta. This goes down to P. And it covers some base map R. So it is P R theta, such that it realizes it makes B essentially the tangent bundle. So theta is fiberwise isomorphism. Is a fiberwise isomorphism, and it intertwines the derivations. Theta star after D equals D after theta star after P star. These realizations, they are locally, they are the solutions to the coframe problems that we talked about in the first talk. So locally, solutions to coframe problems. Namely, if you take EI x mu y sigma coordinates, then we still have our structure equations over here of the relative derivations. So theta I just a pullback of our frame here. We get one forms on P. And our map R has some components A mu, B sigma, and A mu is just theta star of X mu if you want. B sigma is theta star of Y sigma of the coordinate functions. And then in the equation, d theta p star of EI. Those are the EI components of this equation. Can do left and right, see what you get. This is the same as d theta I, by definition. And it has to be equal to the other side. The other side is theta star of d of EI. And this is the same as negative 1/2 CI JK A B theta J wedge theta K. So this is one part of the equation. The other part is d theta star of P star X mu. That's the same as the A mu. And on the other side, we have theta star of D of X mu. So this will be rho mu I A B theta I. So this translates this equation to the original coframe problem equations that we saw in the last talk.
So presumably a realization, right,
Mm-hmm.
is should give rise to a relative algebroid where it's really the tension bundle is involved. So can I just ask, what is the so a realization is like saying that there's a certain type of relative algebra which we're trying to realize this relative algebra as.
Mm-hmm.
There's a special type.
Yeah.
So what is that special type? What would be the simple kind of relative algebra that a realization gives?
Simple.
Like
Do you mean the tangent bundle with the Ram differential? As it's a Lie algebroid, so specifically it's also a relative algebroid. And what you're looking for is a relative algebroid morphism from the algebroid, the tangent bundle, to our relative algebroid.
Okay, but so for example, when you have a realization, you should have in particular, you should have a relative algebroid where P is like playing the role of N, and maybe N is still there, so it's like P going directly to N.
Maybe one thing that could help is to look at the case of ordinary algebroids and what is a realization in that case.
If you take a Lie algebra, a Lie group with the Marikotan form is a realization of the Lie algebra.
So in that case, I would say, if you take the left invariant vector fields on the Lie group, you can recover the Lie algebra. Okay?
Yeah.
So when you say that you have a realization of the relative algebra, that means that relative algebra now can be rewritten in terms of the Durand complex of this thing.
Along the map R.
So
Yeah.
So
Uh-huh.
never mind that you found it as a realization. What is the special type of relative algebra that you can extract from
If you make the identification with Lie groups and left invariant vector fields, you're already using the Marikotan form. So what do you mean by the special type of algebroid that's underlying the story with Lie groups and the algebras?
Normally for the algebroids, you say, here's a new type of structure. It's kind of like the tangent bundle, but it's not. It's a
Yes.
algebroid.
Mm-hmm.
A realization is a manifold, right? That maps down to your manifold.
Yeah.
Such that now the sections of the Lie algebroid are viewed as vector fields on this thing.
Yeah.
So this means that now I don't actually need to know about the algebroids. I just need to know about these realizations, and I need to know about the tangent bundle.
Okay. Yeah.
Once I know about a realization and the tangent bundle, then that captures the concept of the algebroid. Now you're telling me that there's something like this for a relative algebroid.
Uh-huh.
Okay, so in other words, I should be able to use the tangent bundle only.
If you have enough realizations, yes.
So how do we get a relative algebroid from this realization?
You don't get you get an honest algebroid from the realization. If over the map, so for ordinarily algebroids, this realization only lives alongside a leaf of the algebroid. So maybe the object you're referring to there is the algebroid restricted to the leaf. That's just something you can recover from the realization. Is that the correct way to think about it? Is it the way that you think about it?
So what's the relationship between P and N?
It's literally the composition with the projection. That's
And what's the relationship between P and A or B?
that comes from the theta.
So P is equipped with a special bundle over it, which is the pullback of P.
Yeah.
And there's a relationship between that and the tangent bundle of P.
Mm-hmm. Those are isomorphic because it's a fiberized isomorphism.
Okay, so what it seems like is that you have a submersion from P to N.
No, it doesn't have to be a submersion. This is just an arbitrary. This for Lie algebroids. If you take a realization of the Lie algebroid, it lives inside a leaf. It will never be a submersion. Well, only when a Lie algebroid is transitive. But typically, it's not a submersion in general. It's only a submersion over the leaf.
Of the offer is fit between nobody inside the leaf. And an algebroid, it will take a subset of a leaf. And the realization is integration, a local integration of the restriction of the algebroid.
It's almost, right? It's like a source fiber. It's a source fiber, but then you can interpolate along the leaf, and that gives you the entire. Doesn't have to be surjective even. In a way, you can think of this R. So this is our N, and this is our N, and now R cuts out maybe some sort of submanifold, and our B in a way restricts to an honest Lie algebroid, an honest transitive Lie algebroid along this submanifold, and if that's true, philosophically, yeah, it's transitive, except that for the relative case, there can be several leaves or several of these kind of integral submanifolds through the same point. It's even worse because the anchor doesn't have to have constant rank even, so it can get very weird. But philosophically, it's the image of R, if it has constant rank, will be a integral submanifold through which, in a way, the relative algebroid restricts to an honest Lie algebroid.
So what is the structure that we obtain on the realization on P? We get a Lie algebroid. Or what do you obtain on P? as a result of the fact that it's a realization of A.
An A coframe.
A trivialization of A.
No, an identification of TP with A. That's fiberized and isomorphism. And that satisfies specific relations. I don't know what you mean with structure exactly. Also for ordinary Lie algebroids, I also don't understand your question, or exactly where you're going. Like, if this was just an ordinary algebroid, we don't have to think about anything relative. What do you mean by what structure do you get on P? Like local groupoid structures, something like that. Maybe a translation in the fiber directions of R. Is that what you're alluding to?
So there's a few disconnects because there's ideas of realization that I know of, which are different from the way that you're using realization. But basically, the idea of realization for Lie algebroids is that you would like to represent that Lie algebroid as the tangent bundle of something, making it geometric, therefore.
Yeah.
So, for example, in the case of the Lie groupoid, the Lie algebroid becomes like the tangent to the source fibers, something like that.
Yeah.
So now you have a relative algebroid, and now you're saying, I want to realize this relative algebroid, this abstract relative algebroid, as something simple, like the tangent bundle of something. I don't know what the answer to that question is. So in the Lie algebroid case, the Lie algebroid becomes a tangent bundle. In the relative case, it becomes what?
I think it also becomes a tangent bundle.
The tangent bundle of P. This is what you mean when you say that P has an isomorphism.
If you're saying it just becomes a tangent bundle, I don't think that's different for relative algebroids. It's, yeah. The difference is that the relative algebroid, the derivation there is underspecified.
The solution curve that you spoke of before, the integral curve, is that a realization?
It's not the realization itself, it's like an integral manifold, maximal rank. This is the image of R. It does not give, it's not directly a realization itself. It's like if you have an algebroid, you can choose a leaf or an integral manifold. And if you take a realization, it will be it will follow the leaf. So these integral manifolds you get here like the analogs of leaves. For the relative vector fields.
Yeah, for the case of the relative algebra given by a relative vector, yeah, correct.
Yeah.
What would a realization of that be?
That would be an integral curve. And yeah, you can have flat curves of relative vector field. I mean, it can be very weird. But yeah.
But maybe what thing you want to do, but you don't expect to have a realization rate.
Yeah. Realizations are not guaranteed to exist. They're not unique if they exist. There's a kind of uniqueness if you have two realizations. If you have two realizations whose image of the realization map overlap. So here's one Is this big enough? Or should I draw a larger picture? I'll draw a larger picture over here. So suppose you have two realizations. And these are the images of the realization maps. They can do something like this. If they overlap at a certain point, like overlap actually as manifolds, then on the overlap, they're locally diffeomorphic as coframes. Like they're as realizations, they're locally diffeomorphic. You can find a diffeomorphism acting on the right side. Sorry, that's the left side of this realization that intertwines the two different realizations, but only if their image is a manifold and overlaps in the same manifold. That's when you have a local uniqueness. They do not touch each other, can realizations across each other. Wait, yeah, let me just continue drawing this. So these are the images of two realizations, blue and orange. Over here, we know they're locally defined. Here they go through the same point, but they're very much non-unique. They're not intertwined at all. You can even have things touching like this. Maybe tangent. Even when they're tangent, that's not enough. You need them to be, you need their image to overlap like in an entire germ. It doesn't even have to be a manifold. It also can have cusps here. The image can be literally anything.
This diagram, do you have in your mind where n is? Is this a projection down to n?
It could be, this could be M2. It's M.
It's projecting down to n as a subversion onto n? I guess not. Never mind.
No, and I think the actual technical condition is that they should be. I think the overlap has to live in, the overlap has to be the same in N and M. So N, you also have the same curves. And then the overlap has to be really the same. I lost orange here. So it's a quite rigid uniqueness assumption.
So
Yeah.
like in general, I think the fact that P is not trivial.
Sure. For relative algebroids, we like to think of them as submersions.
But like, is there a place that we need subversion property or?
Technically, no, but everything will live in the image of your map. If you talk about realizations, everything will live in the image because realization goes through M. So if you're viewing relative algebroids from the perspective of realizations, everything outside of your image of P does not matter. What about the constant rank assumptions? Is that going to play a role? Yes, that's also playing a role. In the structure that I erased, structure of relative derivations, this whole diagram, this exact sequences, it's only exact when P is a submersion. Otherwise, you don't have exactness. So there it also plays a role. All right. The next example I want to discuss because it will play a role. Well, it's a fundamental object of the theory. It's like the universal, a tautological, tautological algebroid. So in this case, we fix a vector bundle. Yeah, and recall that elements in this derivation bundle, like fiberized elements, can be thought of as derivations relative to the inclusion. So we're going to use this to define the tautological derivations. The tautological relative derivation. It's relative to P1, which is the vector bundle projection from the bundle of derivations to N. So to specify a derivation, we have to specify a derivation relative to P1. We have to specify a section of the pullback bundle, the pullback derivation bundle. And it's a tautological section because D at the point dx, so at the point dx of D, it has to be an element in the fiber of D1 of A. So it can be dx itself. So it is dx. Or if you want explicitly, the check of some alpha at the point dx is defined as dx of alpha, which is now in +1 of A star P1 of, A star of x, which is P1 of dx. So it's a very tautological. It's also universal in the following sense.
What is P here? Like
P1 is the vector bundle projection.
No. P.
There's no realizations here.
Oh, is that what we're reading?
No, it's an example of a relative algebroid. Or maybe the example of a relative algebroid. Because A, B, D is, if this is any, no, let's do realizations first. Let's see what kind of algebra this is. So realization of A, P1, P check. What's the realization of this relative algebroid? It's any A coframe manifold P, any fiberized isomorphism TP A N B and R. A both ring.
Shouldn't P be mapping to the space of derivations, like to D1 curl D1A?
Uh-huh. Yeah, so we need to define a map. So this is like a theta, right? We need to define a map to the space of derivations, and that's what we use the RAM differential for. What we do is D. Oh, this should be maybe Rn, and then we get, once we have this, we automatically get a map to the space of derivations to D1 of A. How? So the R from P to D1 of A is defined as R at the point P. Now we need to specify a derivation, a pointwise derivation. That's all right. So we get theta of P. Well, first we use theta to pull back forms to P. Then we can take the Durham differential here, but then only pointwise you can push it back to A. But pointwise is fine because pointwise derivations are elements of our bundle. So first we go back, theta star composed with D, and then theta star at P inverse. And this will be the composition. And this makes sense because this now goes from forms on A to wedge Wooler plus 1 A Rn P star. So you pointwise push forward the Durham differential. And this gives us a realization of the universal relative algebroid. Let me give you some.
Okay, so what were you planning to do next?
I'm going to say why this is universal, and then come the completing the prolongations. But that may be a topic for the other time, for the next time. Yeah.
Prolongations you will do next time?
Yeah, I think so.
Okay, but basically you introduced all of the main things, the main material that you wanted to talk about here, right?
Yeah.
For this.
For today.
So
Mhm.
I'm just trying to get. So you've introduced these relative algebroids, and then you have this tautological one associated to any vector bundle.
Mhm. Yeah, so why that's universal? So you get A, B, P is any relative algebroid. Then we get a classifying map. And go C, it's determined by the derivation. It goes from M to D1 of A.
The thing is, so I don't mean to be too annoying, but do we really need to understand this universal tautological algebroid and the reason that it's universal? Or is it better that we understand what a relative algebroid really is? I'm asking you honestly for the next talk. Do we need to know the tautological algebroid and its properties? Or is this just bonus stuff?
It's very useful for, it's based around prolongations. Because
In order to understand prolongations, we need this thing.
exactly. Because the prolongation will live in the as a restriction of a universal algebroid. Yeah, if you want to formalize the prolongation procedure. Exactly.
Rather than just define what a prolongation is.
Yes.
Understand what a prolongation is.
Yes. If you want to strike like the universal
Okay,
yeah.
but what I'm more concerned about is that we don't have enough of a concrete example of a relative algebra. So far, the one I have maybe is, yeah, so I'm sorry to like push you off of your course, but try to give the simplest example of a relative algebra that you know. And try to make sure that we get it, because that's kind of important for the next stop.
Mm-hmm.
I'm
Okay.
kind of assuming that there's at least one other person in the room who does not know yet what a relative algebra is. So apologies for my presumption. No. Just give us an example of a relative algebra, your favorite one, simplest one.
There's so many. I really like the relative vector fields that we saw before. We've talked about those, right?
Yeah. Do that one. Yeah. Review that one.
Yeah. Let's talk about realizations of this one and see how many we have. Let's do a very simple relative vector field. It's relative to on R, relative to R2, the projection. I'm not going to use this anymore.
Just explain the simple example.
Relative vector field. Okay. So I'm going to get this coordinates x2, x1, and this projects onto x1. And the vector field is x at the point x1, x2, x1 equals x2, the x1. So we saw this
Energy vector base manifold, which varies in the fibers.
exactly. Yeah. So it doesn't mean that's it doesn't mean that we cannot act on functions that depend on x2. It doesn't mean that if we act at 0, just we cannot act on functions that depend on x2. So the relative algebra that we get are it's over R, we have R2, R, and realizations are integral curves. So gamma t equals x2 t x1 of t such that x1 dot of t equals x2 of t. Okay, can you give me a realization of this algebroid? Or can you give me an integral curve?
Choose x2 to be whatever you want. Let's say we choose it to be a constant c. And then x1 will be c times t plus constant.
Mm-hmm.
So let's just try to draw it. So try to draw the picture. We have a vector field that looks like a shear vector field, but it's not really a vector field on R2. And then the solution for this is horizontal lines.
if you specify x2 of t, then you get an honest vector field, because as specifying x2 of t will be like choosing a connection on this one, because now we have a splitting that sends, so we get a connection. Is it good? Is it good way to think about that? No.
You should x2 and then x1 is the integral of f of t, right?
Exactly. Yeah, it'll just be the integral. I wanted to think of something as graphs, but that's not really. But yeah, we can specify by any function. Let's see if we can introduce the concept of prolongation through this example. We can write on the derivation, so d of dt equals 0, and d of x1 equals x2 times dt. So we can try to extend this derivation. The tilde of x2. We can specify what it is, whatever we want. We can also leave it open as like a independent variable. So we can just make this some sort of x3 dt, where x3 is now a new variable.
So the process that you've started here, you're trying to describe how to find realizations.
Mm-hmm.
So
Wait, okay.
the realization is that you're trying to find certain curves inside R2.
Yeah.
With what additional data? Just curves?
In this case, just curves. Yeah. The thing is, so x2 is not specified in this equation, right? So we can come up with some sort of x dot 2 of t. And suppose we have, there's a way of extending this. So we can choose this any extension. We can also choose a space of all possible extensions. And then this depends on another parameter, x3 of t. There's another function that we can choose. Namely, depends on the derivative now. And you try to complete it, but you have, there's now the derivative of x2 depends on the, well, a new function, which is the equation that you add, it's the derivative of, it's x3. So now x2 is determined, but it depends on its derivative. And then you can go on. You can try to determine x3, but it depends on whatever its derivative is. It's some new function x4. And this is the same as extending your derivation. x3, no, x14 dt. Whenever you try to specify it, it will always depend on something that's not specified.
So when you're adding these variables in terms of your original R and R2, what are you modifying when you introduce these new variables? How is your space or your diagram of spaces changing when you prolong in this way?
So if we prolong on this step, we get a new relative vector field. We get a new vector field x tilde that now depends on x3, x2, x1. But we can only differentiate x1 and x2. So this would be x3 dd x2 plus x2 d x1. That's a new relative vector field that we get from this set of equations.
Okay, so originally you had R2 mapping to R, and you had a relative vector field on R2.
Mhm.
We're trying to solve. You were trying to find an integral curve. Now you've created a new an extension of the problem where you have R3 mapping to R2, and you're similarly trying to find an integral curve.
Yeah, and integral curves of x tilde project down to integral curves of x. I'm thinking if this is this algebroid is the integral curves are very explicit because you can solve it by choosing x2 and then vice versa.
Integrating.
So and vice any integral curve is determined by x2 by this function, vice versa. So in this case, it's kind of clear what the realizations are. I think I want to do a more theoretic example where we don't just have integral curves.
Yeah, but what you've done here is kind of important. For you, it's trivial, but for me, it is not clear what the logic is. So you had this original problem, then you took derivatives, and you increased the size of the problem, right? So you've done a prolongation.
Yeah.
So if you had to explain why you're doing it, what would you say? What is the purpose of doing it?
I find it hard in this example because the integral curves are so explicit. That's
Okay, but principle, even if it's a trivial case, the reason that you're doing the prolongation is in general why? Is it to achieve some simpler form or to put the relative algebra into a different, that it has a different property?
There's several ways you want to do why you want to do prolongations. First reason is there might be integrability abstractions that don't exist here. So that's why you want to compute the prolongation. Second case is your prolongation might be simpler and your derivation might be actually determined for some reason. Here it will never be determined. Third reason, initial conditions. What does it mean to have an initial condition in this problem? We can specify, well, x dot. It's not unique either. I mean, you can specify x1, x2, but you still have many integral curves through each point. So we might want to need more initial conditions. How many do we need? x2. We might try to specify x2 dot, the derivative of x2. But if we do so, we get an extra variable, so we can try to specify that derivative as well. So it's trying to complete a set of initial conditions. That could be a third reason to introduce prolongations. It's just, in those examples, it's so explicit. Because it's about x2. You have to specify a function. If you want to specify an initial condition, a pointwise initial condition, you have to specify the derivative of x2, which will be x3. You have to specify that derivative, which will be the second derivative of x2, or the third derivative of x1. If you continue this, you have to specify the entire power series of x1, and only then you get a solution. That might be unique if you're working with nice enough functions. There's also in in this example, you can already see solutions that, if you start, you have the zero solution starting at 0. So this would be the x2, x1. The zero solution would be an integral curve, right? The zero solution would be the place where the anchor vanishes at 0, at x2 equals 0. In this case, our curve is the rank of the anchor is constant along the curve. We can choose x2 to be a flat function at 0. Then x1 is also flat at at 0. So we have like a solution that starts at 0 and then goes somewhere else. What happens to the rank of the anchor? Well, it's 0 over here, but it's non-zero here. And that's very different from algebroids, where your realizations or integral curves always have the same rank. An integral curve is either constant or it's injective. It's an immersion. These kind of integral curves don't care about rank. And even if you try to, if you do one prolongation, then along x2, you have a space where you have a place where the rank actually becomes 1 of the new relative algebroid, because the x3, x2 now vanishes when x3 and x2 equals 0. But still, those flat functions, they will always provide an example where your anchor jumps rank along your solution. Even if you go to the profinite limit, where you incorporate all derivatives, you have an integral curve from the flat functions, where in the profinite limit, at one point your anchor vanishes, and at another point it's injective along the integral curve.
So when you did this prolongation, right, your diagram of faces on the left, that square, that gets modified, right?
Mm-hmm.
Could you like draw one more step to that diagram? Just to get a sense of what happens to that diagram of Lie algebra on the left, the square.
This square. Oh yeah. So this was our derivation d, and here are R3, and here we have our derivation d tilde.
Yeah. So just and it's important to see how the ideas fit together. So originally you had the first square, and you were presented with the problem of finding a realization, which is like finding integral curves. When you extended the diagram now to the bigger square, what is, so you have a similar problem, and in principle it's like more difficult. It's a higher dimensional problem. Yeah. But you're hoping that maybe it's less underdetermined. It's more determined. And then what's the profinite limit? So you keep doing this forever in sequence. Yeah. Yeah. I'm just trying to prompt you to kind of explain, even in this simple example, what the process is. You start with something simple, very underdetermined, and then you prolong it. And what are you supposed to do after this prolongation exercise?
That's something I'm working on. We get either a Lie theoretic object in the profinite limit, where you have a derivation that actually squares to 0, and then you can try to do Lie theory. Another thing is
it's too quick. That was somehow you're answering my question, but so quickly that I don't understand the answer. So you're saying that in the end, you're going to get a Lie algebra.
Yes.
On what space?
It's on a profinite space, but the algebra itself has rank 1, so you get a profinite vector field.
Okay. So it's a vector field on an infinite dimensional space.
Exactly.
The infinite dimensional space is the set of like all derivatives.
Yes, it's like
path.
Mm-hmm.
Okay. And then the problem is that you're trying to integrate, you're finding an integral curve for an actual Lie algebra, but over an infinite
Yeah.
dimensional space.
Mhm.
So that's what occurred. That's somehow the logic.
Okay,
It's
I
not-
see.
It's not a Lie algebra.
Yeah.
You prolong it until it becomes a Lie algebra.
Mhm. That's
For all the hoping that you have more than solution, you will make these undetermined problems.
it's also about
That happens after a finite number of steps. Or, and then you do have a real, finite dimension. Or. Like, does it stop?
let's write just down the tower. So this over R, this over R2, R3, and this is over RK. This will be over R infinity, the space of all sequences. The reason, well, yeah, you can always hope to have a finite problem, but you still want some Lie theory. So this has coordinate x1, this is x2, x1, this is x3, x1, x2, x1, and this is xk, x1.
Every time you introduce a new variable, you also introduce a new part of the differential equation
Mhm.
that says like it's x3 dots, x3 is x2 dots,
Yeah.
x4 is x3 dot, etc. Yeah. Okay.
Yeah, so it becomes like an
So that's making your derivation. It's
X.
specifying basically the derivation at each stage.
x2 dot equals x3, x3 dot equals x4, and this specifies like d2 and d3 specify, but and it just goes on and on and on.
And when you say that in the end, you get a Lie algebra,
In the end, you get a rank 1 Lie algebroid over R infinity,
and what's the like?
and it's a pro-finite vector field. It corresponds to the vector field x equals sum xk plus 1 ddxk. And that's the pro-finite vector field. Now you can say it's an infinite sum. Do we have to worry about convergence? We're also looking at pro-finite sections of this bundle. So we only act with x on functions that depend locally on finitely many variables. So at pointwise we'll deal with finite sums. It's yeah, it's like that. So yeah, there are two ways to solve this. Either you can say, okay, x1 of t is unspecified. Oh wait, we can choose x1, and x2 is just a derivative of x1. x3 is a second derivative of x1, etc., etc., etc. So we can choose xt, be any f of t, x1 of t, and then xk of t equals kth derivative t. And then we get an integral curve. This is a vector field, so what's its flow? This could maybe hint to a groupoid, right? Flow. It's a little hard.
The flow of a pro-finite vector.
Yeah.
What you're asking about.
Because for the flow, you have a unique integral curve at each point in the profinite manifold. It's a specified integral curve.
Point in the profinite manifold just means a point in one of the finite versions.
No,
Or it's a sequence.
it's a sequence. A specified integral curve for each x. I call it x infinity because
You have to find the flow on each finite level.
there is no flow on each finite level. It's because it always goes up.
In this case, you still wouldn't have the unique integral curve, right?
Yeah.
You still have this problem that you would have to choose the whole first function, not just.
So if you specify initial condition, it will be like x1 of 0, x2 of 0, which is x dot 1 of 0, well, x1 dot of 0, right? So the initial condition is the power series of x1 at 0. And if you want to specify an integral curve, specify a function for each power series. So specify function for each power series. Even local functions. That cannot be done in even a continuous way. Another way of thinking about this is maybe.
So wait, so you're now trying to say that even though we have this algebroid of rank 1 of this profinite space, there's issues still. It's not as if we can just treat it as if it was the usual algebroid.
Exactly. Yeah. We can specify to each integral curve, and then we get a Lie algebroid over the integral curve. We can also look at integral curves of specific rank. So either emergent, injectus, or 0. And then we can look at a place where the algebroid jumps rank. So that's a x1, and all the rest is 0. Then our vector field is 0. Then our algebroid has isotropy. And our realizations have translational symmetry. So the symmetries of our realizations is still encoded in the algebroid. But yeah, there's no flow in the entire space. You can also think of x as like the shift operator. On R infinity. That's the x infinity. The shift operator on R infinity. Let's do S. The vector field corresponding to the shift operator. And then you can look at the e to the power ts to find its flow. It's e to the power ts. And you can try to look where it converges. And converges if and only if your initial condition is a convergent power series. Is convergent power series. And then if you restrict to the space where it converges, this gives you a flow. So it's like going to an analytic resolution. Mhm.
We realized we went over so much.
Yes.
Today, and
Mhm.
we'll do on Monday. Thank you very much for tolerating our annoying questions.
That was good. Yeah. Mhm. Thanks.